What first drew you to the world of chemical engineering and ultimately into semiconductors?
My father, he had a PhD in chemical engineering, specializing in cryogenics. I remember myself from a very young age thinking about what engineering career I'm going to take. Actually, Intel became my university. There is no revolution. There is no complete innovation. It's evolution and quite slow paced.
What would you say were some of the biggest technical or operational challenges that you encountered as, of course, fabs scaled in complexity and, of course, from a technicality point of view?
Actually, my career start coincided with the fundamental shift in semiconductor manufacturing, actually in sustainability in semiconductor manufacturing in 1995. There was a very aggressive goal with the immediate execution plans that industry leaders like Intel and others started to manipulate and develop. Everything gets in the fab through subfab, and everything leaves the fab, leaves manufacturing floor through the subfab. This is a gateway where it's not just equipment and technologies, operations are there, our ability to influence, to reclaim precious materials, to recycle, to treat effectively, everything is in the subfab. Subfab falls between the chairs. Nobody is challenging the status quo. Right now, we don't have a viable roadmap for subfab sustainability. Go crawl and learn. Our solutions are really primitive. Today, in many cases where we understand, we see reactions that are happening of pure materials that didn't react in the fab. I don't know how many of the audience and including yourself are aware of the fact that certain process steps like atomic layer deposition or epitaxial growth, they consume, so you need more etch, you need more deposition, you need more vacuum and abatement. And in these numbers, it is a commodity. And here, the bet is too high, the stake is too high.
Join us as we welcome Ilya Zabelinsky, a leading voice in semiconductor manufacturing. With almost 30 years of experience at the forefront, Ilya's expertise in vacuum and gas abatement is unparalleled.
From his early days commissioning Israel's first 200mm fab to his leadership role at Intel and the establishment of ISRL, Ilya has consistently pushed the boundaries of subfab technology.
Get ready to explore the complexities of this vital field and its impact on the future of semiconductors. Let's dive in.
Hello, and welcome back to the Semiconductor Leadership Podcast. I'm your host, Salah Nasri, and it is with great pleasure to welcome you all today on a delightful discussion, actually, which is very underappreciated in the semiconductor industry, and that is the subfab topic. Joining us is a true pioneer in this space, Ilya Zabelinsky, a globally recognized technical leader with nearly 30 years of experience in vacuum and gas abatement applications for semiconductor manufacturing. So if you're new to the show and you're not familiar with what we do, the Semiconductor Leadership Podcast is a podcast designed to explain to the world what is the latest and greatest in semiconductor manufacturing, leadership strategies, and cutting-edge R&D discussions. So without further ado, if you haven't subscribed, click that subscribe button, because the more followers we get, the more interesting this podcast becomes. Just like our guest today. So without further ado, Ilya began his journey at Intel in 1996, helping commission Israel's first 200mm fab and later driving operational excellence across Intel's global subfab network. In 2022, he founded ISRL. And this is known as the International Subfab Research Labs, on a mission to bring science to subfab. Ilya, welcome to the show.
Welcome, Salah. Thank you very much for having me here.
It's an absolute pleasure, honestly, Ilya. I love covering topics that are kind of underrated or under-discussed, but hold valuable importance. It's like the dark horse, you know?
Black hole.
Black hole, yeah, exactly. So, Ilya, I mean, I want to go, first of all, in terms of your career journey, right? So if we rewind the clock, you've been in this industry for nearly 3 decades. What first drew you to the world of chemical engineering and ultimately into semiconductors?
First of all, thank you again for having me here. It's truly excitement. And my journey actually was under inspiration of my father. My father, he had a PhD in chemical engineering, specializing in cryogenics.
Okay.
Engineering was always in our home, and I remember myself from very young age thinking about what engineering career I'm going to take. But first, I was looking into mechanical area, not specifically chemical or chemical engineering. But after I immigrated to Israel, I was born and raised in Moscow, and at the age of 19, I immigrated. I continued my path to engineering and first graduated my mechanical engineering degree. And after having nearly 2.5 years in the military service, I got an announcement, or actually the Intel was looking for a first team to start up and commission a new location for 200 millimeter factory. This is where I had a perfect timing to join that team and start growing with it. Actually, Intel became my university, and as I was evolving as a technician first, technical leader, I realized that chemical engineering is another area where I need some technical, academical background first, and then I should be able to contribute more to what I'm doing at work. So I graduated my second degree or another bachelor's degree in chemical engineering, all in parallel to work in Intel.
Marvelous. So you know, it's evident that you played a pivotal role in launching Israel's first 200 millimeter fab with Intel. Can you share a bit more about that experience and what it was like to be part of that foundational moment that you were involved in?
This was truly incredible. I can tell you that as a very young recent college graduate, barely 6 months into the job, I received a task from department manager: go and devise a commercial contract with Edwards, a company that we will later buy hundreds of vacuum pumps and gas abatement equipment from them. And it was like, go do your research work. At the time, it was late 90s, was still no cloud or ChatGPT resources available. So I had to write from scratch, collect some pieces from other factories, and write a commercial contract. Again, stuffing it with the all necessary technical details. Again, working in parallel with the Intel buyers, but arranging the operational foundation for the factory. And this is the freedom I really had in Intel. So that's why I'm truly thankful for the opportunity I had for that timing, for graduate to college, finish our military service, and then be able to start a new factory from scratch, take care for everything from very basic things to contractual, making shifts, hiring people. So this is and again, all in parallel with starting up facilities, commissioning systems, dealing with failures and troubleshooting failures.
So just to clarify, was this the first? Was Tower Jazz, were they there before? Or Tower Semiconductor, were they before Intel?
Intel has a very interesting story, and Tower following its path in Israel. So Intel started in 1974 with the development center. First factory was a result of extreme success that Intel Development Center had, and the Intel management, global Intel Corporation management, decided to build first fab outside of U.S. soil in Israel, in Jerusalem.
Wow.
This was Fab 8. It was commissioned in 1984.
Okay.
That factory brought a lot of success and worldwide exposure to Israeli semiconductor and Israeli talent pool. Then Tower has its own history, and I don't want to go too deep, but Tower at the time of Fab 18 construction, first 200 millimeter factory for Intel, Tower had a 150 millimeter factory, 6-inch factory. That was also Intel first factory in Jerusalem, was 6-inch. So first 200 millimeter factory in Israel became a brand new Intel Fab 18, which was a sort of a copy exact construction from Intel Fab. It was a D1B, later Fab 20 in Oregon, was reproduced in Ireland and in Israel.
Wow. So tell me more about, so I'm really intrigued because this is new to me. The development center. What was the development center at? Is it more
Design.
Chip design. Okay. So it's chip design, and what was basically the driver to it? Was it more so to get Israeli students that have graduated from US to go in and study there, or what was the purpose behind it?
Actually, I know quite a lot about Intel. I finished second in Intel trivia for Intel celebrating 35 years of operation in Israel. So I know some stuff. Among the first bunch of engineers and big contributors to Intel's success in the first days was gentleman still alive, Dov Fruman, a legendary person. He led the team that patented the EEPROM. And Dov's success and Dov's drive and Dov's contribution and passion was among the factors that made Intel management, Intel board, to decide to build first R&D center outside of US and specifically in Haifa, Israel.
Wow, intriguing. Okay, so I'm intrigued to, of course, understand over time. Yeah, you took on a global leadership role across Intel's subfab operations. What would you say were some of the biggest technical or operational challenges that you encountered as, of course, fabs scaled in complexity and, of course, from a technicality point of view?
Absolutely. Actually, my career start coincided with the fundamental shift in semiconductor manufacturing, actually in sustainability in semiconductors manufacturing. 1995 was the year where Kyoto conference or Kyoto resolution had been accepted by semiconductor industry leaders, and the commitment was made to reduce global warming gas emissions drastically to the level of 95% by 2010. Emissions had to become 95% less from their level in 1995. So it was a very aggressive goal with the immediate execution plans that industry leaders like Intel and others started to manipulate and develop. When I joined Intel, or Intel Fab 8, the older factory where I had my training in the first days, they didn't have gas abatement at all. There wasn't such word even known to technicians or engineers. My manager, in the first days in Intel, he was on relocation assignment in the U.S., in Arizona, and during our conversation, I asked him, I'm going to be responsible for gas abatement systems. What are these? What's the world? What does it mean? He had no clue. So we learned as we progressed. First gas abatement systems that factory had to install were electrical control decomposition oxidation CDO systems made by Delatec, Napa Valley company, later acquired by ATMI and Ecosys and so on. So they were pioneering gas abatement, actually trying to convert some burner systems from different industry segments, not for specific semiconductors, to abate, to decomposite, oxidize, and wash PFCs out of gas streams. And as we grew, we grew up with the systems. This is where exactly the problem that I'm trying now to address and solve when it started. It all started from sort of a garage scrambling of solutions. There was no fundamental research and fundamental design at the first place. And then when you enter the loop, it's irreversible. You always chase your production levels, your uptime, your commitment, your technology tape out cycles. So there is no time in the entire loop from development to a high volume manufacturing where you can hold on and do some research and come up with the solutions. So as a technician and engineer in a factory, in high volume manufacturing factory, I always had to deal with immature, inefficient, non-reliable equipment that we were getting. We were actually committed to install, since Intel cultivated and still cultivates a copy exact methodology, copy exact culture. So every new factory at Intel builds copies exactly the equipment set, from fab tool to subfab, even facility. So it drives just copying the same problems, having very little flexibility and freedom to deal and address problems, and it's a never-ending story.
Intriguing. So, just to clarify on everything that you've kind of mentioned as a whole thing, do you feel that this kind of garage, I always call it maybe entrepreneurship perspective, has faded because you don't hear of any new gas abatement players or vacuum pump players coming out of the blue anymore? What is your gut feeling about this?
No, you actually can see a very interesting variety of different players, and mature players. They're constantly coming up with some new designs, but new designs for existing concepts, for existing technological blocks.
Mm-hmm.
There is no revolution. There is no complete innovation. It's evolution and quite slow paced.
Right.
And there are companies, and here's the catch: why you don't hear the other names. Everyone knows the market leaders like Edward Sabara, Kashiyama, Bush. There are many other companies in Asia, and it is extremely difficult for them to convince their customers to be that their equipment is reliable enough. And here, the bet is too high. The stake is too high, because once you install a pump, or you don't buy a single pump, you need to equip an entire tool set. You want to maintain integrity among your tool set, because vacuum is an essential supply for process stability.
Mm-hmm.
And you cannot variate between different chambers on the same tool and between same tools of the same cluster of the same kind. So when you buy vacuum or abatement systems, you buy them in large chunks and large clusters to maintain that process integrity and similarity, commonality.
Mm-hmm.
So you can, if you have a problem, you know how to address it. So it drives reluctancy and very strict decision making on who gets in the door. We'll talk about this later.
Mm-hmm.
This is one of the problems or one of the challenges that ISRL is coming to address.
Can I say, I mean, from your perspective, is it now a commodity game?
It is absolutely commodity. Yeah, by all means. So coming back to when I started, Fab 18 was a brand new 200 millimeter factory. It was qualified. It was commissioned to run 180 nanometer or 0.18 micron. It was the latest, the most advanced technology at the day, and it had roughly 600 vacuum pumps, which was a double of what Fab 8, a 6-inch factory, had in Jerusalem. It was like, wow. The modern factory has 4,000 vacuum pumps. it's exponential growth. Of course, it is driven and fueled by multi-patterning, by extreme complexity of processes, very long cycle times, but again, even with EUV, multi-patterning is not going away. So you need more etch, you need more deposition, you need more vacuum and abatement. And in these numbers, it is a commodity. So it actually makes the subfab related initial capital investment so high that companies try to compete for $100 difference on vacuum pump selling price, thus removing any extra complexity or any extra smarts that can be useful in AI age, for example. So today we're all looking towards more aggressive AI implementation for fab operations, for predicting reliability, predicting performance. But subfab is dumb and blind. Subfab has very little instruments and very little analytical equipment involved because of it being commodity. It has to be extremely cheap per piece, so you can buy thousands of these. So this is one of the drivers.
Thank you for the elaboration. I mean, Ilya, I think one would, of course, ask, especially to some of the audience who are not familiar with the term subfab, and it actually just popped into my mind. Could you give us a brief outline on what subfabs are and what it's about?
Yeah. So fab is the building, but fab is essentially a clean room level of a fab building. Everything, the entire building is a fab, but clean room where manufacturing takes place is commonly referred as fab. Many cases, support equipment finds itself too noisy, too chunky, too dirty to consume that white space in the clean room, which leads to the practice of having an extra floor, an extra level, typically underneath the fab. That's why the name subfab, something that lays underneath the fab. Not everywhere this practice is being followed. In smaller facilities, subfab equipment can be just side by side, so just can be installed in the clean room, and there might be some really large utility level for larger facility systems. But it is very common to have a dedicated floor for vacuum, for gas supply, gas abatement, waste collection, waste treatment, and essentially the way I refer to subfab today in connection to sustainability of the manufacturing, subfab is sort of a gateway. Everything gets in the fab through subfab, and everything leaves the fab, leaves manufacturing floor through the subfab. So this is a gateway. Where it's not just equipment and technologies, operations are there, our ability to influence, to reclaim precious materials, to recycle, to treat effectively, everything is in the subfab.
Thank you, Ilya. Now let's get straight to it. The mission behind ISRL. In 2022, you founded ISRL, the International Subfab Research Labs, with a vision to bring science to subfab. What inspired this mission? And most importantly, why then and why now?
Coming back again to my Intel days and to that constant struggle as an operational technician, as an engineer, as an engineering manager, operations manager, always through all these positions and roles in the same space, the biggest burden of not being able to deal effectively with problems associated with equipment reliability or efficiency constantly bothered me. And I came to understand very well the dynamics and how things work inside big corporation like Intel, and I also had a quite good exposure to what is going on in other companies, and things weren't different at all. For several years in Intel, I tried to influence internally and convince executive level management that there is an absolute need for dedicated dealing with subfab R&D. The way the technology itself gets addressed with the sort of pathfinding tools that are that Intel has on in Oregon to deal with the pathfinding, to deal with the technology steps and technology operations that are not relevant for current technology, but they would become relevant for next node. Same approach had to be taken with subfab, and ironically, or not ironically, logically, this is what many companies, including Intel, are doing with larger facility systems. It is in place with the UPW, specialty gases, specialty chemicals, slurries. There is internal R&D for non-fab functions, but they call facility R&D. Subfab falls between the chairs. It always a derivative of process tool selection. It always, like we started, somebody else's problem. It's somewhere there downstairs in black space that not necessarily every engineer gets even to see it. Or working for years in the fab, not everyone really gets to see what's going on in subfab and how this equipment is not serving the needs. So after trying to do this internally, I realized that Intel has way higher problems or larger scale problems to deal with, and it coincided with a very interesting perk that Intel has for employees. It's called Rule of 75. When an age and service time of employee in sum gives 75 years, you can retire. So I celebrated 50. I was 26 years in Intel,
Wow.
and I decided this is the time. And especially I'm convinced that it has to be outside of a single company. It must be collaborative, industry-wide. It should not belong to a single company, and it should not be done internally, because every internal effort makes it very siloed, and everyone loses.
Do you see that? I mean, is there a reason why others are not implementing the same methodology? Are they aware of it by any chance? So, when I refer to others, I refer to like your TSMCs, your Samsungs, your Infineons, your STs of the world.
Again, when I said subfab operations are quite similar, but there is there are some distinct differences. Some factories don't even have a dedicated subfab maintenance team or engineering team. In certain operations, certain companies, subfab equipment is maintained by fab technicians or vendors, and it's a sort of a narrow-minded vision, a tunnel vision, where you have your day job, you have your fleet of vacuum pumps and gas abatement. You know exactly how they work. You can perform routine maintenance. You can troubleshoot, and you don't really ask questions. So this is what you have. This is what you get. This is how it works. And in many cases, problems are taken for granted or as given. This is an unavoidable problem. It's a process related, harsh processes, unwanted reactions. This is the way. Yes, this vacuum pump works only 2 weeks and we need to replace it. This is that's life. This is the cost. Again, companies make quite good margins. They're quite successful. Their primary business is to tape out to meet the demand, and it just doesn't get enough attention and is not translated to the impact to fab operations, to its profitability. And of course, today we're more concerned about sustainability, where the biggest hit is coming.
Why do you feel that they don't see it as a high priority? Is it really that the case that they're so focused on the bigger picture that they're
Absolutely.
neglecting?
Several reasons. First, they see big picture. These numbers are numbers, quite significant numbers, but they are all factored in and they are still making money. So, and it's been for years. So why change? Second is that there is a belief that nothing can be done different. Vacuum pumps today, they must be very, again, there are several process variants. There are light duty applications and there are harsh duty applications and medium duty. And if we disregard the light duty, the load locks or processes that run in inert gases where no reactions are taking place and there are no byproducts, solids or liquids or any coatings are not generated, then pretty every vacuum pump out in the market will perform nearly equally. There are no big differences. There are some form functions. There are some mechanical complexity functions. But in terms of reliability on light processes, most of brands and models they perform similarly. On harsh duty, this is where the difference come in. And then, but even the best products on the market, on very harsh processes, they suffer very short lifetimes. There are processes where vacuum pumps get full and seized from operate in a matter of days, weeks, few months, and this is where most of companies say, okay, this is what it is. We tried Edwards, we tried Abara, we tried Bosch, we tried Kashiyama. Everyone has the same. So this is what it is. Nobody is challenging the status quo. Nobody today, again, and I say nobody, I don't want to hurt anyone's feelings, but, and I'm really welcoming somebody just to join our effort and try to bring the difference, bring science. And by saying bringing science to Subfab, I don't know if right now is a good timing in terms of the flow of the interview, but later I would like to give an example where science will make a difference.
Sure. So for our listeners who may not be familiar, can you explain what ISRL does and how it's different from so-called traditional subfab support models?
Yeah, absolutely. First of all, it is not about support.
Okay.
International Subfab Research Labs plans to build a playground, something that IMEC did for the industry, and I constantly look at IMEC as a role model, even at their history. IMEC's history started with the initiative of several engineers coming from Silicon Valley to their home country, Belgium, explaining the need to the government, to the university staff, that there is an urgent need, and we talk about late 70s and beginning of 80s, to have a playground which is not at somebody's yard, something standalone that will welcome research, will have all the infrastructure required for research and development. So today, technology research and development, technology pathfinding, roadmap of semiconductors, there are several places in the world that deal with that. Same IMEC, Leti, Fraunhofer, and other RTOs around the world. None of them have the ability, have the freedom to deal with subfab, something which is not in the fab. So subfab in many terms means dirty or dangerous. Reactions taking place in the subfab, they may really jeopardize performance of the process tools. So if you run very, very delicate, very, very precisely tuned machines to develop gate all around or other groundbreaking technologies, you don't want your machinery to be involved with something dirty or dangerous. That's why existing infrastructures like IMEC, like LEDs, theoretically they could host this kind of R&D, but they are reluctant to do so. They do some of it, but not to the extent and to the depth required. So we are aiming to build a facility, or actually develop a facility, which will have all infrastructure required to run like a fab. It will have machinery or process tools very similar to what typical fabs have, and this equipment will be solely dedicated for subfab related R&D. No product, no machine time dependence on factory commitment, on factory resources, and this dedication and focus will open will become a playground. Will open opportunities for innovation. Startups that today struggle to get in the door of a big companies, big factories, they will have place to go and innovate and test their solutions.
I see. So, as you mentioned, basically subfab is, of course, often considered as an invisible infrastructure. I think that is the best way to describe it. What would be interesting to understand is aside from it being dirty and dangerous, why is it so critical to semiconductor manufacturing? And if dangerous and if dirty, what are the risks if we don't innovate in this area?
Let's start from sustainability. Sustainability it has different pains, and one of the most common and well known is carbon neutrality. So companies today are taking aggressive goals, aggressive commitments on carbon neutrality. Carbon emissions, they come as equivalent of global warming gas emissions, gases used in etch, gases used in chamber cleaning and deposition, and several other process steps. Existing technologies, most of them still use some sort of fossil fuels, either natural gas or LPG. Some of them use electricity, which is a direct scope 2, translated to scope 2 carbon emissions. And even if they use today plasma, they still require some amount of energy. So these all not good enough. We absolutely need to look for greener types of ways to abate. For example, harnessing biotechnology, enzymatic destruction of PFC molecules. This is just off the top of my head an example of what should be explored towards those goals on sustainable manufacturing. Moreover, as I mentioned, at certain point there are no differences between equipment performance delivered by different manufacturers. It might be a plasma abatement or a thermal wet abatement from one supplier or another. They all suffer low availability figures because of very primitive or substantial clogging of unwanted reactions of byproducts of materials that are coming into abatement before they even reach the location inside the system where they undergo abatement. They tend to react and clog. This problem companies constantly fail to effectively address, which renders their equipment availability very low. In other words, there is a very nice and fancy abatement system there, but it's available only 50% of the time. So other 50% either gas leaves the factory unabated, or the tool which this abatement system serves stays down, which enormously drives capital cost, capital investment that factories need to make. In some cases, they need to double their tool base to compensate for that low reliability of abatement systems, and in many cases vacuum systems as well.
Which is good news for the abatement system supplier, not the vacuum pump supplier as well. I mean, that's sales for them, right?
At the first glance, it might be perceived like that, but at the end of the day, I believe the prospect of the growth for the industry is way bigger than that short-sighted advantage of selling more because there are problems. Because if we don't solve these problems, industry won't be able to expand to that projected 1 trillion or beyond, because it will be putting out so many emissions. It will be so energy hungry, and it will exceed available capacity for energy and for and regulated gas emissions. So it won't be able to expand. It will grind to the halt. Very much like industry slowed down because of next generation lithography wasn't ready in time. Subfab equipment readiness, sustainable subfab might become that showstopper for the industry growth, but without roadmap.
Right.
At the time, lithography at least had a roadmap. There were delays. Right now, we don't have a viable roadmap for subfab sustainability.
Why is that?
And again, I don't want to pretend I can explain all the mechanisms of how things are working in different organizations, but it looks like that siloed approach in many organizations where technicians, engineers do their job. In many cases, subfab job is quite hard, so people don't stay long enough in subfab. People change roles. People don't go deep. It doesn't become their passion. In other cases, engineers and managers they evolve and go up the chain, and they not necessarily realize what are the true problems, the true mechanisms for that are slowing down, that are breaking things apart. So there are several people very few people in the industry that see the whole picture, and there are even less who want to do something about that. This is what our team is trying to do. We're trying to change that. We're trying to highlight for the industry where the problems that not necessarily others see, and once we get more people to see them and understand and agree, we want them to join us and make it truly collaborative and available for large community.
So I would be intrigued to know from your experience then, what would you say is the number one biggest challenge facing the subfab environment today? And I'm going to say in terms of 4 specific areas. In terms of, is it from the perspective of vacuum systems, gas abatement, energy consumption, or emissions?
Everything is connected. So again, we're not whiteboarding here, but if I would be whiteboarding, I would show you how everything is connected. And actually, when I pitch for the need for subfab R&D, I don't even call it subfab. I call it materials handling from process to the environment. So everything on that way, a vacuum that removes the process materials from process tools, from process chambers, then it pushes us downstream to exhaust, and in many cases this exhaust gets abated in different ways. And then there are emissions and there are liquid wastes associated. So everything is so connected, and everything in every station of these connections, in every joint and every piece, there are so many things we don't know, that because we don't know them, our solutions are really primitive. Today, in many cases where we understand, we see reactions that are happening of pure materials that didn't react in the fab. I don't know how many of the audience and including yourself are aware of the fact that certain process steps like atomic layer deposition or epitaxial growth, they consume no more than 10 or 20% of the pure substances being injected in the tool. Nearly 80, sometimes 90% of the gases, they are very rare gases like germane. 90% of germane leaves the process chamber unreacted, unconsumed, and then later on just gets either solidified or liquidated and dissolved in abatement waste system, and then just leaves the factory in the fractions of parts per million that nobody knows today how to collect. So we waste precious metals, we waste materials, and we also cause significant reliability problems through these unwanted reactions. So our toolkit today is extremely primitive. In many cases, we purge. We use nitrogen. And nitrogen is cheap. But people don't understand that after certain consumption of nitrogen, factory needs another air separation unit to be built across the street, which comes at cost, but not just a one-time cost. It's constant operation of that air separation plant across the street, which is extremely energy hungry. So nitrogen consumption, about 80% of nitrogen that factory gets goes into subfab, trying to prevent those unwanted reactions, trying to flush all these unwanted particles and byproducts that are being accumulated. So we consume tons of nitrogen, really unaware of the energy footprint or the carbon footprint associated with it. And in many cases, this nitrogen really doesn't help. So in other cases, thermodynamics being considered, and then in certain cases, heating these lines brings some relief. Heating vacuum lines or exhaust lines became very common, but in cases where even if it helps, not necessarily it always helps, but even if it helps, it comes at a huge cost of energy. Heating the lines is not just the power you need to apply to heat the lines. It's the fact that these heated lines have insulation, which is extremely inefficient, and external temperatures can get up to 50 degrees C. And it means huge heat load to the factory that needs to be removed by HVAC, by air conditioning. So factory heat load dramatically increased through the heating of process lines or exhaust lines, or vacuum pumps or abatement inlets, and in many cases this is really not being catered or not being attended. People don't realize, or engineers don't realize, that clicking the fingers and saying, okay, we have a problem, let's heat it, fine, and the cost down the road, operational cost for the factory, energy cost, is not being even calculated.
I mean, there's clearly, it's amazing, this explanation that you've provided us, Ilya. But it's evidently that someone is not holding the accountability of all of this waste of chemicals that are out there. What is the solution to all of this? What is the solution to managing all of this waste of chemicals that's just being chucked away or not recycled effectively enough? How is this going to be handled?
So again, there are so many fundamental pieces of knowledge we are missing that we need to start first by researching.
Okay.
And research talent is available. We just need to highlight. There are some parallel areas of research that can be applied to subfab, but nobody so far didn't highlight, didn't turn the beacon for these research teams. Once you work on this problem, if you just shift a little your focus and your end result, you can deliver, you can create a solution for a segment they never even thought about it. They don't know it exists. I'll give you an example, and I already mentioned biotechnology. There is a startup that I came across that they know how to use AI to engineer enzymes for specific task, and I specifically had a very interesting talk with their CTO, asking a direct question: if they can engineer an enzyme that can break down a PFC molecule, and the answer is yes. So the research teams that are working on engineering enzymes, creating enzymatic reactions, they don't know there is a PFC abatement need in semiconductor industry that they can also help to address. They're addressing different other problems with food industry, drugs, all different kind of fields. They never heard of that need in the semiconductor industry. Another example would be a catalytic generation of clean hydrogen, a research done by Rice University in Texas. So their goal is to create clean hydrogen, but they are breaking down H2S molecules. H2S molecules resemble bonds that also exhibited by some edge gases. So working with the same team on a different task, using their knowledge, can bring us to create solutions that right now are not being even looked at these spaces.
Yeah, that was going to be actually one of my the next key question was, okay, so now that you've explained one form of innovation, what other kind of innovation or process improvements are most needed in the subfab space to overcome current limitations that we have today?
I'm coming back to the same thing. Everything will have to be born through the knowledge.
Okay.
Once we start filling these gaps, and again, it's not one shot, and it is a research and innovation that will have to synchronize with technology development. We should not be looking for solutions for today's problems. We should start moving this research and development of subfab, of abatability, of ability to avoid unwanted reactions, to reclaim materials for next generation materials. Those are today being researched for next generation technologies. This is the only way to effectively deal with the problems I mentioned earlier.
Mm-hmm.
Because if we keep dealing with these problems by doing more of the same, we will fail.
So from that perspective, I mean, you've clearly made it very evidently clear in this podcast, the desperate need or the biggest problem that the semiconductor manufacturing industry is facing, acknowledging that sustainability matters, are not going to be fulfilled until the subfab element is being fixed, which is basically pretty much the invisible. I don't know, maybe it could be the wrong analogy to use, but it's like cancer, right? If you don't fix it now, the problem's just going to spread and it's going to be a massive issue later on in time. And we won't hit that specific target, as you mentioned, of $1 trillion. Now, I know that you've worked on some methodologies in terms of trying to get this out there to enable ISRL, which is pretty much, for me, sounds like a platform for knowledge-based gathering research on effective forms of use of subfab development processes that are going to be used around the world. So how is ISRL doing with regards to approaching with fabs, equipment manufacturers, and also one would say governments as well?
Yep. So again, we're not reinventing the wheel in terms of business model. We really, I really admire what IMEC is doing, and I think we just need to do very similar thing with dedicated subfab R&D. So we are aiming to create a facility that will be equipped with everything that is required to run process tools like they are in the factory. Again, cooling water, power, gas supply, exhausts, everything. And this is a playground where we will be holding or launching several programs. Not necessarily all of them will be research related. Some of them will have a research aspect. Some of them will have a very, very clear development acceleration aspect. Current development cycles are extremely slow because if you get to develop your innovation in somebody's factory, you are at mercy of their priorities. If factory, even the most advanced and the innovative management teams or engineering teams, when they welcome an innovation, sometimes they have other business priorities that contradict. So your innovation is always secondary to their primary business goals. So by providing access to a dedicated infrastructure, we can accelerate the cadence of innovation. And this is not necessarily research that will happen and will be connected to our infrastructure. Research can happen somewhere else. They will come, or a company or startup will come with their product, with their technology, just to validate it and test it for HVM-like condition and environment. So we'll be forming there will be several programs, and each program will have projects. Each project will be run like a project with a project manager that will create a triangle: budget, schedule, and scope. And this project will pull in all interested parties. So in many cases, these parties will be as diverse like you named them: equipment manufacturers, chip makers, gas manufacturers, valves and seals, pumps and abatement, all different parts of supply chain. Governments will come into play when the research subject is clearly sustainability affiliated, and then this project is eligible for applying for government grants. There are several geographies that offer dedicated programs for sustainability-related innovation. So this is where government support will come into play. Will be certain very, very clear goal. There will be product or technology that its development will be enabled by ISRL facility. Because if ISRL wouldn't exist, this technology development there is nowhere to happen. So by enabling it, we will provide an ability for that team to apply for government grants and involve government support.
I see. So, I mean, how's it going at the moment? Are you working on any joint research initiatives or pilot projects at the moment?
Yes. I really appreciate the interest we received from CAA Leti, specifically Sir Lauren Payne. He is a director for sustainable microelectronics at Leti. And our recent collaboration just gains momentum. There will be a space available for a small scale subfab R&D infrastructure that Leti is right now considering to create. And we are at the quite early stages, but it looks very interesting and very promising the way this infrastructure will be able to support a larger scale programs like Genesis. There is a large scale innovation program in the European Union called Genesis. There are many companies are part of that program, They received EU funding for sustainability in microelectronics for innovation, and several programs or several several functions of it will absolutely need subfab focused infrastructure.
I see. Marvelous. Now the real question is do you believe that the subfab industry, from a research and development point of view, is receiving the attention and investment that it deserves today? And if not, what needs to change?
Absolutely no. It didn't receive any attention so far. I can feel this changing. I believe after 3 years, I'm trying to expose this need. It's already quite significant exposure happened, and I have to admit that nearly 100% of interactions I had with people, including yourself, it is extremely positive towards the need and understanding, and in many interactions this is an eye opener. In many interactions it's like, yeah, you're right, we're banging our heads for a long time. It's long overdue. Something needs to be done. And you know how this in life, there's so many general statements: should be done, it should be done. When people say should be done, somebody needs to step up and do it. So this is what I'm trying to do.
So from that point of view, Ilya, what's next for ISRL? Are there any upcoming projects, partnerships, or specific elements that you're particularly excited about?
Yeah, given the fact we're progressing well with the pilot approach in France, in CA Leti, our initial goal is to create a standalone facility, a fully scaled facility, and we are fundraising for that. And just recently, there's some significant progress in that direction as well. And honestly, I believe we're just very near the tipping point. And after we reach that tipping point and we raise enough capital to create first facility, I think it is just a matter of very short period of time when that facility won't be enough. Right. The need is so big, and the amount of things we can address there is so large that I strongly believe we will overfill the capacity of such facility that we're envisioning. Again, it cannot be extremely large, and it is better not to be very large. It should become sort of a satellite type of facility that will have to be replicated in several geographies, near manufacturing clusters, near university centers in Europe, in Asia, in United States, and there will be coordination among these, but in each location there might be some specific projects that it should be able to do over ability of others. Okay. And I'm very optimistic these days. We really gain interest. We gain understanding that this is something that industry needs. And like you said, so far there wasn't enough attention, there wasn't enough investment. I hope the things are changing for better.
Ilya, it's evident that you've, of course, had a long and impactful career, but you're still going on. You're still pushing. What's motivating you? What's pushing you to get this subfab passion of yours out there?
Honestly, somehow it really became my true passion. And I have other passions in life. I have 4 kids, and I really enjoy spending time with them and contributing to who they are and how they grow up. And I volunteer in local police. I have other passions, but long term of service and dedicated work on subfab, on vacuum and abatement, really left me, didn't leave me and kind of didn't leave me watching from the side. I don't like to be someone who watches from the sidelines.
Right.
I love to lead. I believe I can do it, and I think this is what we all need. The industry needs, and I feel energized and excited of being able to do this.
So what would be interesting is if you could give one piece of advice to a young engineer entering the semiconductor field, especially in an area like subfab, what would it be?
Go crawl and learn. I just I'm in process of reading a book, The NVIDIA Way, and I really I really feel connected to the way NVIDIA CEO, famous, legendary Basin, the way he was described as being ready for every meeting, knowing every detail, fluent in everything. It is not just for subfab engineering, and it is not just for engineering. It's for everything. The perfection that I strongly feel that I must have when I talk about something, or when I do something. And for many engineers entering semiconductor industry in general, and subfab specifically, unfortunately, there is no easy way to gain knowledge. Even a technician, subfab technician, will take about a year to come up to speed and be qualified. Engineer sometimes don't have that passion for that year, so he finds himself skipping some stages. But there is no way you can skip. You need to be hands-on in your first years of young engineer. As much as hands-on experience will open your eyes, will open your mind. You won't be able to come up with ideas, innovations, solutions if you don't understand how things work. So deep understanding of how things work is essential.
Thank you, Ilya. I mean, we always end this show with a tradition that the last person leaves a question for the next person. And the question that was left for you is what gets you up in the morning?
My family.
Okay.
Family first. And then once systems are checking up and start working, then the fun I'm having of being able to promote, to go after my dream. This is something I say thank you, God, every morning, that I had that courage and that drive and ability to leave. Some call Intel golden cage. It's not so easy to leave at age of 50 a company that you're well paid and you're successful and you're well recognized. And for me, this was extremely important to prove myself I can do it. And I'm happy I'm doing it, and I'm enjoying even these interactions like what we're doing right now. It's part of what I'm doing, and this is what gets me up in the morning.
Marvelous. Ilya, it's been an absolute pleasure to have you on here on the Semiconductor Leadership Podcast. Is there anything that you want to leave out there for the audience that you feel like we may have missed out on in this podcast, in this interview that we've had together? Is there a message you want to put out there? Is there something that we've missed out on, or do you think we've covered everything?
I know there is a gentleman here in the audience that writes a book. Mm-hmm. So I want to advertise this book.
Okay.
Once it's out, I would recommend reading it.
There you go. It's coming out very soon. Appreciate it. Ilya, it's been a real pleasure having you. Your work at ISRL is, of course, it's shining a much needed spotlight needed in the subfab world. Thank you for sharing your story and insights with us. To our listeners, if you enjoyed today's episode, you can reach out to Ilya directly. His LinkedIn is just right here and below. It's the best way to reach out to Ilya on LinkedIn. Other than that, please don't forget to subscribe. And until next time, keep building the future one chip at a time. My name is Salah Nasri, and thank you for tuning in on the Semiconductor Leadership Podcast.
My pleasure. Thank you very much.